Hello, student. Precalculus chapter 1, section 6. I think we're going to do section 7. There it is. Functions and their graphs. Page down. Library of parent functions. Linear and squaring functions. We've been studying this. We said linear mean a line. Squaring, that means quadratic. Parabola equation. All of this I'm skipping. We covered them in previous chapter. The most important things today is the parent functions, the basic simple functions. There is functions that are really basic, very simple and basics. The first one is fx, function of x equal x. That's the simplest line equation. So remember, the line equation was y equal mx plus b. Here, for this problem, m is equal 1, b equals 0. That's the simplest basics. So that's the reason we call it the parent one. Then we can derive all other lines from this basic one by adding a b, by adding in a slope. We can get new lines. So that's the reason we call it the parent one. This is for the linear parent one. The next one is the squaring function. Fx equal x squared. This is with our second order squaring function, parabola. And you can see this is the basic simplest one. That is the parent. And normally, if we plot it, this point here, the lowest point is 0, 0. So the vertex at 0, 0. Because when x 0, if 0 equals 0. So that's where is your vertex. And, and facing up. Later on, we're going to learn how to generate a new equation from the basics one, from the parent one, by shifting them around. There you go. That's the drawing. The next one is the cubic function. The cubic function, that's the basic simplest form, is x to power 3. That's a cubic function. It's again here, f0 equals 0. And that is the vertex of this one. That's vertex. How do you plot it? We need to remember the shape of this one is very easy. It's look like, I don't know, flat S. And this is here is 0, 0. Normally is better than symmetrics. We saw this before, so let me try and make a better one. Uh, that's the x cube. The parent function, the simplest basic one. Here, yeah, there is a better drawing in the book, where x and y go from negative infinity to positive infinity. So another one, a square root. So this is another basics parent function. And remember here, x should be greater or equal 0. Positive. Then what's going to happen, your fx only there is, and for this one, there is no negative y or negative fx. Okay. So we're going to see look like a half the drawing. However, f0 again, let's look for the vertex. It's equal also 0. So this is your vertex, 0, 0, vertex. If we plot this one, this is the 0, 0. We're starting from here. Remember, x must be positive. So we're only going this way, positive x, and y only positive. So we're going this way. So we're gonna, it is gonna look like that. That's the square root of x, basic parent function. We have to go from 0 to positive infinity. Here we go. Yes. 1 over x, a little bit more complicated. It looks simple, but to plot is a tough one. The main reason is we cannot divide by 0. There is no vertex, no vertex. Because f0, 1 over 0, that's going to give me infinity. Large number. Normally, if we're approaching the 0 from the negative side, then 1 over 0 from, that's going to be negative infinity. Where 1 over 0 coming, approaching from the positive side, that's equal positive infinity. What we're talking about, this is your 0. From this side, we call it negative 0, and from this side, positive 0. And you can see we're having a jump in the value. We were here as the negative infinity, then we jump to positive infinity. And really the shape is like that. That is 1 over x. Don't worry about it much how this happened. We'll see this later on. But this is the basic 1 over x. This one is, I'm skipping this part. Excuse me. And skipping this part. That's all of this is, we see it only once, so I'm going to skip it. Summary of parent functions. This is also kind of like when we say fx equal constant, that means horizontal line, that fx equal x, basic line. We didn't look, this is absolute. We don't deal also with that type. Maybe we see it once or 2 times in the class, but this is another basic function If it's absolute x, then what happened for this line, when it's absolute, it's going to do this instead of coming straight. Square root of x, parabola, or squaring function, a cubic function, 1 over x. This one, forget it. So this is section 6, is really short. It's all about basic parent functions. Let's go to section 7. In this one, we are going to learn how to generate a new function from the parent function by shifting them around. Transformation of a function. They call it transformation of a function. We're going to have transformation along x, transformation along y, and we're going to have reflections upside down. Shifting a graph. Now, let's take an example. We're going to take this example. Function of x, that's the basics. Square, parent. Okay, that's the basic. Now, we're going to create a new one. Shift a graph up by 2. So we're going to get a new function. A new. Well, I'm not going to use f. We're going to give it a new name. G of x, x squared plus 2. So shifting up, I added 2. That's it. That's a new function. If I have to plot this, this is the original. Going from 0, 0, this is the x squared. Now I'm going to shift it up by 2. So I'm going to move the vertex by 2. And this is a new location. This is x squared plus 2. All what I did, I moved the vertex. Basically, all the shifting is going to happen to the vertex. Well, it's going to be for every point, but the easiest one to move is the vertex. So each value of y, it's going to be added 2 to it. That's shifting up by 2. Can I shift down? Same thing, like shift down, let's say by 1. The formula, I'm going to get a new formula. H function of x equal x squared minus 1 because I'm going down. So all what I have to do, so this point here is 0, 2. So the vertex was at 0, 0, now at 0, 2. Now for the second one, this point here is 0, -1. I shifted down. So this function x squared minus 1. So it's pretty easy. In y direction, shifting up or down, just add the number. A little bit confusing when we shift along x. Let's say here, shift to right by 3. So let's do the plotting first. We can do that plotting easy. So 1, 2, and 3. So we move the vertex. So that's the original. Okay. That's the x square. And we move the vertex to this location, 3, 0. So that's the new, we shifted, just moved it to the right by 3. However, when we write the equation, let's call it A, we said Gx, you could name it anything. Let's say, call it Z of X is equal. The process like that, you open parentheses first and put the power on top of it. Okay, you put the power on top of it. That's first. Then you put X inside. So put, and because we're going to the right, believe it or not, I'm going to use negative sign, -3. You will understand the reason later on, but you remember, when you go shifting along X, if we're going to the right, you put negative sign. So that is the formula. Shifting to the right by 3. If I say shift to left, let's say by 2, then you can say V of X. Always you have to write a new function because they are not the same. Open parentheses, put the power, whatever the power, could be 2, it could be 3, it could be 4. Then inside you put X plus 2. That going to left. So if I said here 1 and 2, that's a new location. So this one here, x squared of plus 2. This is x squared minus 3. So now we shifted up and down. We shifted left and right. One more operation. So this is shifting up by 2. That's shifting to the right by 2. And the last one more thing that's really easy. Reflection. About X. So remember, the original was fx equal x squared. The reflections, I'm going to call it function Rx. Oh, let me clear. The reflection is equal negative. You put negative sign x squared. So basically, if I have, that's the original x squared. Reflections, like x is your mirror. So it's going to be down like that. That's negative x squared. We know that. We said when x is positive facing up, when x squared negative, we face down. We know that from before. That's a reflection. Can I combine all move? Yes, we can. Let's say I say shift the same function we're talking about here. shift of up by 2, right by, let's use 3, reflect and reflect. Yeah, we always start with right shift. This is a new function. Let's call it V. Let's call it C combination, C of X. So I open parentheses and put the power, put the X. We're shifting to the right by 3. I have to say -3. Now we're shifting up by 2. Outside here, we said 2. We said we reflection, we put negative over here. That's the entire formula. Well, let's plot it. What is negative? This is 3 and 2. The 3 and 2, that's the location of the vertex. So the vertex really at 3, 2. Because we're shifting right by 3 and up by 2. That's the vertex location. So if I say 1, 2, and 3, 1 and 2. So that's the new location of the vertex, 3 and 2. So we moved from here. But remember, we are having reflections. So we're going to write it down this way. So that is the new function. Negative x minus 3 squared plus 2. So we combined all moves. Now here they said if the basic is fx equal x cubed, a graph and sketch these functions. Or first need to figure out where is the vertex. Now we said x cubed minus 1. So what does this mean here? This is down. Did we move along x? No. So the vertex is 0, -1. That's the location of the new vertex. Initially was a 0, 0. So this is your function because this is the x cubed. Now we moved down by -1. This is 0, -1. So we cannot just redraw it again like that. This is x cubed minus 1. It's not too hard. How about this one here? The next one, hx equal x plus 2 to power 3 plus 1. Well, it seemed like, did we shift here left or right? Remember, when positive, we're shifting to the left. So this means left by 2. Here, up by 1. So what's the vertex location? because left, that means negative, comma 1. That's the vertex. So basically, I can use the same graph here. So I need to find this location. So this point 0, 0 is going to move to negative 2 and 1. So that's the new vertex. Or they have to redraw everything over here. So this here, that is the x plus 2 power 3 plus 1. That's the new location. And this point, the new location of the vertex. Negative 2 comma 1. Now let's assume, let's plot another one on the same example. Let's call it Vx negative x minus the 3 cube plus, no, let's use negative, so we can draw it, negative 3. So where is the vertex? The vertex at, because this is negative, we're going right at 3 comma negative 3. That's the vertex. So 1, 2, and 3. 1, 2, and 3. So here is the vertex, 3 comma negative 3. Well, how do I draw it? Because I have a negative, it should be reflections. So what happened? You're going, so this point is going to flip to here. And this, the bottom one, flips the other side. So basically, you do it this way. So that's the reflection. You could reflect it. We said about x, I'm sorry. So this point would go down. This point would go up. So that's what we did. So this point went up. We're going all the way down. So that what happened when we reflect the cubic function. You can see this is one drawing. We already talked about reflections. We are ahead of the book. That's another example. They give us x to power 4. So the original function, if I have to draw it here, see when you have really high power, it looks like a parabola, but have a big flat bottom. So this x to power 4, and this is the 0, 0. We change the color. All right, they are asking us what the equation of the graph in A. Well, just look at this, and we need to figure out shifting left and right, up and down, reflections, whatever we see. The way I see it, if this is 0, 0, then we moved up by 2. So the new function, g of x, equal x to power. Well, did we shift to the right or left? It seemed like we did not. So shifting left or right is 0. So I don't need to worry about it. So I'm going to say x to power 4 because there is no shifting left or right. Now we shifted up, we say plus 2. But this is upside down. I put negative here for reflection. That's it. You put negative in front of it for reflection. You plus 2 for moving up. How about this one? H of x. We move to the right by 3. Did we move up and down? No. So when shifting right or left, I open parentheses, put the power, then x. Because I moved to the right by 3, I'm going to say -3. So this is 3 here, -3. That's it. Oh, that's it? Is this upside down? Ah, okay. I think I have to put negative sign in front of it. Why? Because for the reflection. So remember, don't put it in front of the x. You have to put it in front of the parentheses to be correct. So the negative sign in front of the parentheses. If you don't have shifting left and right, then directly in front of the x. Okay. Here's the solution. You don't need to worry. Non-rigid transformation. See, what we've been doing, we call it rigid transformation. That means I was moving the graph from location to location without changing the shape. The shape is still the same. It's just like, let's say it was here, I moved it to here, I moved it to, I flipped it, it's still the same, and moved it to here. No matter what I move it, it's still the same shape. Did not get bigger or get smaller. So that's why we call it rigid. So it's kind of like stiff. It does not change. Well, what does it mean non-rigid? So if I have the function fx equal x squared, let's start with this one. If I told you new function g of x equal 2 times of x squared. Now we are making the graph 2 times bigger than the previous one. How do we plot this one? We're gonna draw the x-axis, y-axis. If this is the original, x squared. The new one we said we're going to multiply. So if I take a point here, distance, any value, x1. So what is the value of the y? So right now, the value here, this one here, that's x1 squared. But how much is 2x1 squared? You multiply by 2. So this point is going to move to here. So this distance now become 2x squared 1. So if I take another one, I'm going to multiply it by 2. So this is going to be here. If I take 1 over here, multiply by 2, the new location here. The new location is here. So if I connect, what happened with the graph? It got narrower and sharper. So it's getting narrow. So that's the new one. That's the 2x squared. So the shape change is not the same shape. Got skinny. Now let's try a different one. Let's say I have v of x squared divided by 2. Let's see what happened. We're going to do the same things. If this is the original, oh, it doesn't look good. Let's try it again. Then we'll do the same thing. I'm going to take a point here. This is x1. This value here, x squared, regular x squared. Now, if I divide it by 2, then I'm going to go halfway. If I divide by 2. So take another point, divide by 2. Take the same thing, divide by 2. So if I connect, what happened to the graph? Got flatter. This is x squared divided by 2. Got flatter, open out. It changed the shape. So that's what happened. If you multiply by 2, divide by 2, whatever. If you multiply, it get narrow. If you divide, it get wider. Here in the book, they have different example using an absolute of x, still the same things, but I like the parabolas better. Here you can see you can get sharper, narrow, skinnier. Here's get flatter if you're looking at the dark lines. So section 7, finish. Let's see if there is any practice problem. We can look at them. Well, we do have the problem number 2 here. This is about shifting. This problem number 1 really is belong to the next section, section 8. So we'll look at it later on, but you can practice the problem number 2. All right, we'll stop here for the next chapter, for the next section.